This is the recorded version of a talk presented at SIGMOD 2026. My name is Wolfgang Gatterbauer, and the focus of this talk is a principal solution to the disjunction problem of diagrammatic query representations. Assume I tell you that I see a car that is blue and that has a flat tire. What I mean is likely something like this image. Now, what do I see if I say I see a car that is blue or that has a flat tire? It's actually not at all clear. What about this? Not really, because now we see two cars. We need some symbol to indicate that those two cars are alternative options. Also, this on the right side is a white car. We rather want to show something like this. But isn't it surprising how difficult disjunctions become for images? This is very different from, say, relational algebra. There we just have to flip one single symbol. But actually, even in relational algebra, conjunction is a bit different because we actually don't need a symbol for conjunction. Conjunction is the same as just applying two filters, one after the other, so we don't need any symbol. Whereas for disjunctive information, we need some dedicated symbol. As Soonchun Shin states in her 95 book on the status of logical diagrams, any given situation only displays conjunctive information. In that book, Shin focuses on the monadic fragment of first-order logic, and the review states that she showed that disjunctive information can basically not be represented in any diagrammatic system. Thalheim stated that there was no simple way to diagrammatically represent Boolean functions. Almost 60 years ago, Martin Gardner, in his book on logical machines and diagrams, stated that there was no simple way to represent the logical statement A or B implies B or C. And over 100 years ago, Charles Sanders Peirce pointed out how difficult it was to show nested disjunctions, even for monadic logic. He proposed some solution, but that increased the size of the diagram exponentially. Think nested DNF to CNF transformations. This paper solves the disjunction problem. Concretely, every well-formed expression in two-dimensional calculus has a corresponding representation B diagram that preserves the semantics and is of linear size in the original expression, even with arbitrarily nested disjunctions. The solution in a nutshell, we start from UML notation, familiar from ER, entity relationship diagrams. We add nested boxes that show individual negation scopes. Predicates get their own independent anchor. This allows predicates to live in a separate negation scope from the two operands. The representation uses a visual trick that we call Peirce shading that simplifies the reading, namely every negation scope gets shown in alternating gray or white. And then it uses what we call De Morgan fuse boxes to recover explicit disjunctions. So this example states, for all tuples in R, there is a tuple in S that joins on either A or B. We add a dedicated output table for queries. This means statements with 3 variables. Here, for example, return tuples from R for which the earlier statement holds. For details, please see the paper. For the rest of the talk, we focus on intuition behind the solution. Here we see R and S, so that's a conjunction. For negation, we use a dashed closed line that partitions the canvas into two zones, inside and outside. The inside is negated, the outside is not. And this is inspired by the notion of a cut by Charles Sanders Peirce. We then use alternating shading to indicate the polarity of a zone. Everything outside is monotone. One negation leads to a negative or antitone zone. Double negation is again white or monotone, etc. So we can arbitrarily nest disjunctions. Here, for example, now we have nested negation scopes. And for this particular case, we have actually a shorter name. It is material implication. So whenever we have a nested zone with a further nested zone, then the once nested zone implies the twice nested zone. Here, R implies S. Let's continue our nesting. What is this? That is just disjunction. Remember De Morgan. And notice, if we use the alternating shading, then this expression is again monotone in R and S as expected for disjunction. Now notice that we have partitioned the canvas into 4 zones, but the gray zone is actually empty. So we can just shrink it, and we can shrink it further. And now we have alternative adjacent boxes as alternative options. And we call this the Morgan fuse boxes. Now, notice we didn't have to introduce any primary dedicated symbol for implication or disjunction. We just started from conjunction and negation and introduced alternating shading for negation. And by merely reinterpreting the symbols, we have gotten a justified yet derived symbol for disjunction that we can still perceive as a primary symbol, we as humans. Okay, so that was propositional logic. What about first order logic? So for first order logic, let's interpret R, that means R is true, as there exists a tuple in R, and similarly for S. Then, step by step, the expression R implies S is the same as for all tuples in R, there must be a tuple in S. Great. Okay, so we have already been in first order logic all the time, and we still have the same interpretation of nested zones. The outer first nested zone implies the inner, the second nested zone. So let's make this more interesting. We make this more interesting by adding attributes. Yeah. So now each of the tables R and S has attribute A. Now we have something that looks like a more familiar query. For each tuple in R, there exists a tuple in S that joins an attribute A. So let's combine these two variants. Can we do this? No, we can't. This is not well formed. R and S are not bound in a shared scope. A predicate must be inside the scopes of both table occurrences, and this is not the case here. R and S are siblings. We can't just create a predicate between siblings in the negation hierarchy. That is not a valid expression. Let's look at this issue in terms of zones. On the left side, we have 3 zones, Z1, Z2, Z3. R is in Z2 and S is in Z3. The predicate is also in zone 3 and is therefore inside the scopes of both table occurrences, R and S. On the right, we have 4 zones. Now, R and S are no longer nested. They don't share any zone. So we cannot have a predicate that references both R and S because there is no zone that lies within the scopes of both table occurrences. What any formalism needs to be able to express is the case where the predicate sits deeper in the nesting hierarchy than the 2 tables it references, as in the case here, where we have the predicate behind another negation. So we need the ability to place a predicate in a deeper descendant zone than the 2 tables it references. In other words, each predicate needs an independent anchor that determines the zone where it lives. In our diagram, that anchor is the predicate label. And this label can be nested further, as we see it here. So with this gained ability to place predicates independently, we can now reinterpret the earlier reading of predicate edges as a visual shortcut for the case that happens frequently, especially in SQL, when the predicate resides in the innermost scope shared by the tables it references. With that, we can now see how this helps us diagram arbitrarily nested disjunctions. Let's return to an example from earlier. Every tuple from R joins with some tuple in S, either on A or B. Recall that the De Morgan fuse boxes are really just a visual shortcut for something more complicated, expressed purely with conjunction and negation. The formal semantics of these predicates is defined using what the paper calls anchor relations. Each predicate is interpreted just as an equijoin with an appropriate anchor relation. And the paper first defines the formal semantics using these anchor relations, then simplifies the notation using the predicate anchors discussed earlier, And finally, applies the visual shortcuts, Pierce shading and the Morgan fuse boxes. Now that we have all the tools, we can solve one of our earlier puzzles. Our original puzzle by Martin Gardner. His statement, remember Martin Gardner was a master of mathematical games and logical puzzles, and he said there seems to be no simple way in which the statement A or B implies B or C can be shown in a diagram. So what Martin Gardner did, he proposed to use Venn diagrams. This is a Venn diagram that says that the shaded area means this is not possible. So whenever we have X, there must also be Y. But it's a composite statement. X is now A or B and Y is B or C. So that's the proposal by Martin Gardner. So can we now make this simpler? Yes, we can. And here it is. That is the solution. Notice the sparsity of symbols and the compositional character. The gray zone implies the white zone, and the gray zone is A or B, and the white zone is B or C. This is one atomic diagram. There is no K-split. Also notice that what we see is actually a visual simplification. It has a lot of complexity. If we went back to the primitives that we started with, conjunction and negation, all nicely packaged up, similar to the way that disjunction implications are just shortcuts, obstructions for us to reason and to simplify the reasoning. So takeaways from today. We now have a principled diagrammatic representation that allows us to diagrammatically represent arbitrarily nested negations. Every well-formed tuple rational calculus expression has a representation B diagram of linear size that preserves the semantics. And as the paper shows, the exact same atomic leaves of the abstract syntax tree of the tuple rational calculus expression. And there's also the relational pattern. In a recent CIDR paper, we extended that with representations for groupings, aggregates, recursion, bag semantics, and a generalization of tuple relational calculus to what we call abstract relational calculus. A tutorial at SIGMOD this year discussed the vocabulary for a question that will become increasingly important. How can languages help humans and machines read, write, understand, and modify queries, especially in a future in which we have a database interaction where queries are written by machines and read by humans? Thank you for your attention, and please reach out or leave us feedback.